Okay, good morning. Let's start. So today we would like to discuss the creation of design matrix regressors. Or columns, because that's the same thing. Design matrix columns for fMRI or GLM fMRI. However you want to call it. So it's a bit of a long title, but that's essentially what we wanted to discuss. So remember from what we discussed previously that in fMRI you typically present an experiment and you have these event onsets that you record. So a participant is lying in the scanner and you present some kind of experiment. And at a given point in time, you present some condition, for example, faces or houses or high valence and low valence stimuli, all of this. And then we last time discussed that this basically is replaced by a predicted form of the volt signal, or the MR signal better, by basically putting a hemodynamic response function wherever there was an onset of the event of interest. And if you remember from the first day when I showed you how to analyze fMRI data or to statistically model fMRI data in SPM, you saw that I at one point put in some numbers. So these were like 10, 20 and 50 or something, which are the time points after the beginning of the run of these events. And then you basically click create design or whatever you click, you basically click run, and then SPM and any fMRI imaging data analysis software will do this convolution step. And or this replacing event onsets by predicted MR signal time series. MR signal. And you of course also remember that these predicted MR signal time series then are the columns of the design matrix, and if you look at them from above, you see this typical picture of a design matrix which has these kind of bands of bright things wherever there's a peak in the predicted MR signal. And so we've seen this, and another thing that we've seen and discussed in the neurocognitive methods course was the idea of a linear time invariant system, namely that this whole experimental setup of stimulation and then neural response, and then hemodynamic response, let's call it HR, and then MR signal, that this to a degree behaves as a linear time invariant system. So do you remember when it doesn't behave as a linear time invariant system? So there were some boundary conditions essentially when this doesn't work quite well anymore. Okay, it's like 5 weeks ago. Well, it doesn't work quite as a linear time invariant system anymore if the duration between stimuli, so the interstimulus interval or the inter-event interval, becomes too short, because then you have adaptation processes and the response to the second event is not as strong as to the first event. So there were some, so remember there were these late 90s experiments where people tried to predict from the response to two stimuli how the 3-second stimuli, essentially how the response to 6-second stimuli is, and so on. And then they also looked at how basically the response to a single stimulus is if you make the interval, the stimulus interval shorter. And from this, it basically they followed that and one can follow that the whole system of stimulation, neural response, hemodynamic response, and MR signal behaves as a linear time invariant system. if the events are separated by between 5 and 8 seconds or something, then it works. And both of these ideas are so one on the one hand that you replace the event onsets by a predicted MR signal by putting hemodynamic response functions wherever there was an event. And the idea that you can do that because in a specific way, because the whole system behaves like a linear time invariant system. These are typically then, or these underlie the fact that what is done to create these predicted MR series, meaning the currents of the design matrix, is that the event onset functions are convolved with their hemodynamic response functions. And this is what you typically find in FMI papers. I hope you read some FMI papers by now, where it says something in the method section, event onsets or stimulus onsets, onset functions were convolved with a hemodynamic response function. Or the canonical, usually it says something with, were convolved with the canonical hemodynamic response function. So this is usually one sentence in typical FMI papers, where they do GLM analysis, where they then use random field theory to infer on the peaks and clusters, or whether they use this as a pre-processing step for doing some classification. They usually, if they do a GLM analysis, it will have contain the sentence event onset function will convolve with the canonical hemodynamic response function. And so what we want to do today then is basically look into the theory of what this means, why it's done, and what's behind it. Yeah?
I always encounter this word canonical, but I don't know what it means in this respect.
Yeah, this is why we're doing this course. Good. But actually the bigger question is not so much what the canonical is. This just means that it's the conventional hemodynamic response function that everybody uses. The bigger question is what convolution actually means, because that's canonical hemodynamic response function is just a specific type of hemodynamic response function. But the question is why use convolution in this setting? And what is convolution? And how can you program convolution? And is it a good thing? And what happens if you convolve things? So these are the actually interesting questions about this. Good. And to do this, we will basically go a little bit into the theory of linear time invariant systems. And before we talk about linear systems, we first have to talk about mathematical formulation of time series data as data as real valued sequences, so that we know the mathematical entities with which we're actually dealing here, so that we know what we're talking about, which is always a good idea. Oops. Then we will introduce the notion of discrete time systems, because this term system is often used, but the question is what it's supposed to mean, and it means something specific in this context. And once we set up discrete time systems, and specifically linear time invariant systems, because of course that's how the whole stimulus, neural response, hemodynamic response, MR signal sequence is modeled here, because there's experimental evidence from the late 90s that this is a good idea. Once we have established that, then we talk about convolution. so that you know what is actually happening in SPM when you click Create Design. And once we're done with that, we actually might talk about the canonical HF. So yeah, I think that's the plan. Anything I'm forgetting? I don't think so. Yeah. Good. Any questions about this at this point? No. Good. Then let's just dive right in. So first we have to talk a little bit about real-valued sequences, because in the current setting of talking about the columns of the design matrix, we view the time series that we are creating here, that is meant to predict the MR signal as a regressor in the GLN. We view this as real valued sequences, and it makes sense to establish a little bit what we mean by that. So we'll write a sequence X and mean by it something like this. Doesn't really say much, but this will be a sequence, and these Xi are the elements of the sequence, and each Xi is just a real number. No? These are just real numbers. And then we can distinguish different kind of sequences. So we can have finite sequences where I essentially, you can view it always I going from 1 to a number n. And this is, of course, the scenario that we are dealing with in real life, in kind of when we have a computer and we have our event onset function and we create a regressor, then we have a finite sequence of these regressor values. But if we talk about it in theory and how the theory is developed, it also makes sense to talk about infinite sequences, where which are of course just approximations to very long sequences, so we don't care about that they end. We deal with infinite sequences, and in this case we just take I to be an element of the integers. So remember, the integers are all the negative integers, 0, and all the positive integers, going to infinity, negative infinity, and positive infinity. And this is what we are dealing with. If we are dealing with finite sequences, you might as well view these as elements of this vector space. Of course, if we're dealing with infinite sequences, it's a bit more logical to think about infinite sequences as mappings from the integers to the real numbers. So then in this case, in a sequence, an infinite sequence is something like a function from the that allocates to each integer value, it allocates a real number. So to make this concrete, let's have a look at a finite sequence. So if we, for example, talk about this, we have a sequence with 7 elements. So each xi here is called, or sample, you can call it sample or element. That's the ith element of the sequence, or sample. And we have here 7, oops, that should be x0 here. And now, of course, these x minus 3, x minus 2, x minus 1, x0, x1, x2, x3, in a realistic setting, they of course take some values. So, for example, 4.5.2, 1.0, 2.6, 3.1, 1.7. So, and this would be like a real example. So it's just numbers that are ordered. So it matters in which order they appear because they are allocated to each of these integer values. And then one can visualize them. So maybe let's also look at that. So here's an example of a visualization. To scroll. No.
It's first level design.
No, thanks. So here in A, that would be an example. This is of course not what I just wrote down, but a little bit different. So -3 has here some value around 5, -2 has a value around 1, and so on. So this would be how to visualize such a discrete sequence. Of course, often you would also basically connect these dots, and then if you look, for example, at MR data, which is also, of course, discrete because you sample a data point each time point, and in the design matrix, of course, you also have discrete entries, because remember that there are n rows, as many as there are time points. But if you connect these dots, then it looks a little bit more like something that you're used to. But because it's discrete, it actually makes sense not connect these values. Good, so that is essentially, very roughly the idea of a sequence. So remember that we basically have to deal with infinite sequences for the most part in the beginning. One thing that we can add here is that if this is n-dimensional real space, you can view this as z-dimensional R space. So you have basically infinitely long vectors in the real numbers. Okay, questions about this basic definitions of sequences? No. Good. Then the next thing we need to be able is to somehow compute or calculate with these sequences, because we later on, of course, want to convolve them. Because we will, of course, consider our event onset function as sequence. We will consider the hemodynamic response function as sequence, and the convolution will also be a sequence. So when we want to convolve convolutions, of course, this will rest on some other sequence operations. And the sequence operations that we need in particular are addition. So the question is, what does it mean to add two sequences? And let's assume that we have two finite or infinite sequences, x and y. Then we can define a third finite or infinite sequence, x plus z, which is given by x plus y. Of course, you can only add together two finite or two infinite sequences, because otherwise you would not know what to do, because the addition of these two sequences is defined in an element-wise manner. So the ith element of z, the sequence z, is given by the ith element of x plus the ith element of y for all I in z. Yeah? So if you have two sequences that are either both infinite or both finite, of course, if they are finite, they need to have the same number of elements. Then the sum of these is given by the sum of their elements. Yeah? But of course, if they are finite, they have the same number of elements, and if they're infinite, then for each z you have specified the value of x and the value of y, and you can also specify the value of z.
Sorry for interrupting. So in which settings we use finite or infinite?
Well, in real life you always use finite, because the data is finite. In the theoretical discussion of this, because you want to basically discuss it for all possible cases, and then also include infinite, because why not? So in the theory that we're doing here, we will in the beginning mainly use infinite sequences, and then later on go to finite sequences, because that's real life where we have finite sequences. The other thing is scalar multiplication. So if we have a sequence x, and we have a scalar, so not a sequence, but just a number, just a real number, then we can define a second sequence as the multiplication of a times that sequence. And this essentially just means that the ith element of y is defined as a times the ith element of x for all indices. So for example, if you think about this sequence here, which is of course again a finite sequence, actually we can make it infinite if you want, by not talking about everything that happens outside here, or setting this to 0. So if we say everything, so if x minus 4 to minus infinity and x 4 to plus infinity, they are all zeros, then we have just created an infinite sequence. And if we now talk about multiplying this by some scalar, so for example by 2, so if you said a equals 2, then we would have 0, 0, 0, 0, and then 2 times 5.2, 2 times 1.0, 2 times 2.6, and so on, and from here on then again all zeros. So that's scalar multiplication. So these sequence operations are really straightforward, because they work in an element-wise fashion, and of course they necessitate that the sequences are of the same type. If they're finite, the same number of elements. If they're infinite, they're both infinite, that's fine. And then you just can do these element-wise sequence operations. Questions about the operations? No. Then we need a specific type of sequence, which will be quite important for this whole convolution business, namely the Unitsample sequence, or the notion of Unitsample sequences, because there's not only one. The kth, so we're considering the kth Unitsample sequence. And this we define and write like this. So there's this delta with this superscript k. This is a sequence, so it comprises elements, or samples. Yeah, but let's call them elements. And I is of course again the index, and can again be in general be an integer. And now the important thing is that the delta, the ith element, so the delta I of this sequence is defined as 0 for I not being k. So k is one integer, but it's only one. So for example 3. and I is the index of the elements of the delta sequence. So I runs from -infinity to +infinity in an infinite case, and it's always 0. So whenever it's not k, it's the element delta I here, this element is 0. Only if I equals k, then it's 1, and this holds for all I integers and all k integers. Yeah. So for a concrete example, let's look at delta 4, so the 4th unit sample sequence. And if we, for example, plot the entries here, and we start with, let's say, -2, so that's our I here, -2, it's, let's first put the indices down. -2, -1, 0, 1, 2, 3, 4, 5, 6, and now let's put down the values. What's the value for -2? So what is delta I? 0. Yeah. For -1? And for 0? This down, that makes a little more sense. And for 1?
1.
Isn't it the 4 case for?
It's a 4, yeah.
Okay, so then it's 0 again.
That's a 4 here. So for 1, it's 0, and for 2, and for 3, and for 4. Yeah, exactly. And again, it's all zeros. So it's everywhere 0 except for the number that is indexed here. Yeah, and of course, one unit sample sequence that we will come across is the unit sample sequence with a superscript 0 that has a 1 at 0 and zeros everywhere else. But yeah, basically this shows that there can be, no, it cannot be, that of course the 1 can be anywhere, depending on this k. Yeah, so the k says where the 1 is, and everywhere else it's 0. Good, and based on this and the notion of adding sequences, we can also already establish one important thing, namely that we can write all infinite sequences as sums of weighted unit sample sequences. And this looks as follows. Let's give it a name, representation of sequences So what we have is essentially a sequence X, and we assume that this is an infinite sequence. And now, based on the elements of this sequence, so the xi, and the fact that we can scalar multiply a sequence and we can add different sequences, we can rewrite X. Don't go away. We can rewrite X as follows. So this might look quite harmless, but you really should think about what this means. So this is here a sequence. this is the ith element of x, and xi is a scalar. Yeah, so that's a real number because it's just an element of the sequence. It's a scalar. So what we have here under the sum symbol is actually the scalar multiplication of this ith element with a sequence again. So this is a sequence of all zeros except at delta I, where it's 1. And then we add all of these scalar multiples up. Yeah? So we basically multiply infinitely many unit sample sequences that all have their ones at different i's. We multiply all these unit sample sequences with the respective scalar entry of the original sequence, and then we add them all up, and then we get our x back. Yeah. So for example, so to make this clear with like 3, let's use -1, 0, 1, and 2. So if we have, for example, these elements here, and let's assume that this is 2 and this is 4. So we have the sequence 2, 0, 4, 2. Then what this says is that we can also express this as a unit sample sequence with a 1. So the 1 would be here with a 1 at -1. And we multiply this by 2. It has zeros everywhere else. And plus let's just write them up first. So this would be the one that has a 1 at 2. This would be the one that has a 1 at 3. And this would be the one that has a 1 at 4. And the first one we had to multiply with 2. The second one we multiply with 0. The third one we multiply with 4. And the third one we multiply with 2. And then if we add all of those, then because each time we basically multiply this 1 with the respective entry of x, we get x back. Yeah. So that's the meaning of this representation. And that's also quite important because we will need that representation for the convolution theorem later on. Questions about this? You don't need to write all of this down, but if you want, do it. Because it's all in the script essentially. Good, so that was basically talking about time series data as real valued sequences. So of course, these are now sequences which you can use to model anything that is in some kind of order, so the sequence could also be over space, but of course here we're interested in data points and regressor entries that are ordered in time, and we've seen that we can add such sequences, we can scalar multiply these sequences, and we can represent any sequence by an infinite sum of unit sample sequences, where the unit sample sequence is just the sequence that has a 1 at its defining k value and zeros everywhere else. Good. Then the next thing to introduce are discrete time systems. And discrete time systems are just functions. So if you are happy with what functions are, then you're already happy with discrete time systems, because these are just functions with a specific domain and a specific range. Namely, the domain are sequences and the range are sequences. So discrete time systems map sequences onto sequences, and we will write them here with a T, which is the conventional way they are written in systems theory. So they take, in general, they take in an infinite sequence and map it onto some output infinite sequence. We wrote a sequence as an x, so we write the output of this as tx. No? So it's just a function. So a system is just a function, deterministically assigns some output sequence to some input sequence. That doesn't mean, so what is important here is that it doesn't necessarily mean that these functions work in a element-wise manner. So it does not mean that the function is defined necessarily by mapping each of the elements of the input sequence to a specific element of the output sequence. But it might also, each element of the output sequence may depend on all elements of the input sequence or none. So a somewhat stupid example of a discrete time system would be a discrete time system, let's call this that maps any sequence, so x maps to tx, that maps any sequence onto the unit sample sequence with a peak with the 1 at 0. That's a little bit stupid, but that shows that the entries of the output sequence not necessarily depend on the input elements that the elements of the output sequence do not necessarily depend on the elements of the input sequence, and specifically not in a element by element specific manner. It's just a very stupid example, so you can immediately forget about it. A little bit less stupid example is a so-called accumulator system. Which is a running example in the script, because one can show specific aspects of systems quite easily with this accumulator system. So an accumulator system is a discrete time system, so a function from the infinite sequences to the infinite sequences. Of course, you can also define these discrete time systems for finite sequences, but we do this in general here with the infinite one. And this works as follows. The accumulator system, for each input sequence, it of course specifies an output sequence, which we now call y. And the important thing is that here the yi, so the ith element of y, is defined as the sum of all elements. Oops, no, it's fine. Of all elements of x up to point I. So let's briefly look at that. So if we have an input sequence -1, 0, 1, 2, and this took the values 1, 1, 2, 1. So that's our x here, and everywhere else it's 0, so that's an infinite sequence. Then if we look at y, so that's x. We look at y, and assuming that everything else is 0, we can actually also talk about these points here. So what's the value of y for -2 if y is defined like this, and everything else here for x beyond this here is 0? So what's the value of -2 for y?
0.
Exactly. Because that's all infinitely many zeros added up. That's what's the value of there's of course not something to help you here. What's the value of y minus 1? One, exactly. And what's the value for y0? Y1? Y2? And if you're supposed to add them according to this formula, so you get to 2. And what's the value at 1? 4, exactly. I'm running a little bit out of space here, as you can tell. So we have 4. And what's the value at 2? And what's the value at 3, 4, 3, 4, and so on? Yeah, because then only zeros will be added. So that's, if you want, that's your drift diffusion model for decision making, because that's all, these are also thought of as accumulators of the evidence that is represented in area and T or wherever. Yeah. Good. Then I would suggest we have a break now. And after the break, now that we have introduced discrete time systems, look at the definitions of linear systems and time invariant systems. So let's continue at 5 minutes to 9.